Welcome all. In last lecture we have seen the introduction of multiplexer. Today we will see the types of multiplexers. As we know or as we studied, the multiplexer is having many input and only one output. Depending on the status of select lines, the multiplexer outputs any one of the input. Now we will see the types of multiplexer. The first one is 2:1 multiplexer. It is having two inputs, for example named as a D0 and D1, and only one output. As there are two inputs, n is 2. Therefore, using this formula we can find out number of select lines required for this multiplexer. So 2 is equal to 2 raised to m. Comparing the powers of 2, we will get m is equal to 1. So we can say that the 2:1 multiplexer is having a one select line. This is the block schematic of 2:1 multiplexer, which is having two inputs D0 and D1 and one output Y. And as there are two inputs, it is having only one select line, which is named as a S. Now one more pin is there, E input or enable input, or it can be called as a strobe, which will enables the multiplexer. Unless and until we provide a enable input to this multiplexer, it will not give any output irrespective of status of select line. So before making operation of multiplexer, we have to provide a enable input signal to the multiplexer so that it can operates as per its functional behavior. Now we will see the truth table of multiplexer. It is shown over here. Here in first case enable input is 0, that is now multiplexer is disabled. So irrespective of status of select input, as we will not get any output on the output line. So when enable input is 0, we will get a 0 output by default. Now after that, so from this first case we can say that we have to make enable input high so that we can get output with respect to the available inputs on the input terminals. So in second case, enable input pin is made high, select line status S is 0, so multiplexer will select a D0 line, and whatever data is available on D0 line, it will going to appear onto the output line Y. In next case, enable input is again 1. Now select line is made high, that is 1. Therefore a D1 line gets selected as select line is at 1, that is high logic high level. Therefore D1 line gets selected, and whatever input is available over the D1 line, it will gets reflected onto the output line. This is the detailed diagram in which again enable input is shown 0 irrespective of status of select line, irrespective of data available over the data input lines. We will get a default output 0 as enable input is 0. For rest of the 4 cases enable input is made high, so whatever data available over the D0 line or D1 line, it will get appear over the output line. So for this case, a select line is 0, so it will select a D0 line. Whatever data available over the D0 line, it will going to appear as it is on the output line, irrespective of data available over the D1 line. Again, in the next select line is 0 and D0 line is now 1, so 1 will appear over the output line Y. After that, in this case, a select line is made high, by which a D1 line gets selected and data available over D1 line gets appears on the output line. So here D1 line is 0, we will get 0, D1 line is 1, we will get 1, irrespective of D0 input. So for 2:1 multiplexer, when select input is 0, it will select D0 line, and when select input is 1, it will select a D1 line, and data available over the input line appears onto the output line. From this truth table, we can write a Boolean expression. While writing Boolean expression, consider only those outputs for which output is high. So in this case, output is high. For that, E is 1, S is 0, and as S is 0, a D0 line gets selected. Therefore, the first term written is E S bar D0. As S is 0, S is shown as a S bar. So for this one, E is 1, S is 1, and as S is 1, a D1 line gets selected. Therefore, the term related to that is written as ESD1, and combining these two terms, you will get a final output Y, and from this a E variable is taken common into the bracket. We will get S bar D0 plus SD1. From this, a realized or logic diagram of 2:1 multiplexer is drawn. This is a S line, this is S bar line, D0, D1 line and D0 line. To get S bar D0, S bar and D0 are connected to this AND gate. To get SD1, S and D1 line are connected to this AND gate. Combine them, we will get the term which is available in the bracket. And to get E into the term available in the bracket, we used another AND gate. Enable input is connected to that, and the term inside the bracket we get over here, that is connected to the AND gate, and we get final output. From this diagram, we can observe if enable input is 0, irrespective of data available over here, we get 0 output. As we know, AND gate will give 0 into anything 0. So to get a output, exact output available at the output of this OR gate, we have to make enable input 1, by which we get a actual output available over the data input lines. This is how a 2:1 multiplexer can be designed. In the similar way, a 4:1 multiplexer is available, in which there are 4 input lines and only 1 output line. The 4 inputs are D0, D1, D2, D3. As there are 4 inputs, N will be 4. So using this formula, N is equal to 2 raised to M, we put 4 is equal to 2 raised to M. We write 4 in the form of 2 raised to power, that is 4 can be written as 2 raised to 2 equal to 2 raised to M. Comparing the powers of 2, we can get M as a 2. So to the 4:1 multiplexer. For the 4:1 multiplexer, there are two select lines S0 and S1, four data lines D0, D1, D2, D3, and only one output line Y. Here enable input is also available, but in block diagram it is not shown. For every multiplexer, enable input is compulsory, without which we will not use the multiplexer for our application. So this is regarding 4:1 multiplexer. Now you will see the truth table. A short truth table is drawn over here. This select inputs S1 and S0 and a output Y output. Now here first case the select lines S1 and S0 are at 0 0, so it will select a D0 line, and whatever data available on D0, either it may be 0 or 1, it is going to appear over output line. When S1 and S0 are 0 1, it will select D1 line, so we will get a output from D1 line. For 1 0, it will select a D2 line, we will get a output of D2 line, and for 1 1, it will select a D3 line, and we will get a D3 output over the output line. So if you observe status of select lines, 0 0 gives binary equivalent 0, therefore it selects a D0 line. 0 1 is having equivalent number of 1, therefore it selects D1 line. 1 0 having equivalent value of 2, therefore it selects D2 line. And finally 1 1 will use a equivalent decimal of 3, therefore it select a D3 line. So from this the output equation is written. For D0 we should have S1 S0 0 0, therefore S1 bar S0 bar D0 term is written. For D1, S1 is 0 and S0 is 1, therefore S1 bar S0 D1 term is written over here. For D2, S1 is 1, S0 is 0, therefore S1 S0 bar D2 term is written. And for D3, S1 is 1, S0 is 1, therefore S1 S0 D3 term is written, and by adding all of these terms we get a final output Y. The same is realized over here to get a final output using basic gates: AND gate, NOT gate, and OR gate. You can observe this diagram as per this Boolean expression for 4:1 multiplexer. Now here 8:1 multiplexer, third type, which is having 8 inputs and only one output. The 8 inputs are from D0 to D7. As inputs are 8, the value of n will be 8. Using this formula we can find the number of select lines. Here 8 is n equal to 2 raised to m, 2 raised to 3 equal to 2 raised to m. 8 is written in the power of 2 raised to power, in the form of 2 raised to power. Comparing power of 2, we can obtain m is equal to 3. So for 8:1 multiplexer, there are 3 select lines: S2, S1, S0, and 8 input lines D0 to D7. Now here in this 8:1 multiplexer, these are 8 inputs, 1 output, select lines, and enable input. Now we will find the output expression. Again a short truth table is taken over here. In first case enable input is 0, So irrespective of data available over the input line and irrespective of status of select lines, the output is 0. Now as there are 3 select lines, the number of combinations of select inputs will be 8 from 0 0 0 to 1 1 1, and for all these 8 combinations enable input is made high so that the multiplexer can operates. Now here S2 S1 S0, for first 0 0 0 the decimal equivalent is 0, therefore it will select a D0 line and we get output with respect to D0 over output line. Next is 0 0 1, its equivalent decimal is 1, so we will get D1 line is get selected and it appears over output line. Next is 0 1 0, that is its equivalent decimal number is 2, therefore D2 line gets selected and appears over output line. For 0 1 1, its decimal equivalent is 3, therefore D3 line gets selected and appears over output line. In the same manner, for 1 1 0, decimal equivalent is 6, D6 line gets selected and appears over output line. And for last 1 1 1, its equivalent decimal number is 7, therefore D7 line is selected and appears over output line. From this truth table, output equation is written. E enable input is taken common from all the terms. For this first combination, this S2 S1 S0 are 0 0 0, therefore the first term is written as S2 bar S1 bar S0 D0, as D0 line gets selected for this status of select line. If we take this second one, the S2 S1 are 0 0 and S0 is 1, so S2 bar S1 bar S0 and D1 term is written. In the same manner, all the remaining 6 terms are written over here. This is our final output equation of 8:1 multiplexer. Using this output equation, we can draw a logic diagram of 8:1 multiplexer, which will give outputs with respect to status of select line and data lines. In the similar manner, you can design 16:1 multiplexer at your own. This will be your homework. We have to submit the realization of 16:1 multiplexer to me on or before 29th October. So for 16:1 multiplexer, you have to design at your own. If not possible to you, refer TechMax or textbook for the design of 16:1 multiplexer. You can easily solve that using the textbook. Thank you.